Up next, Solar Mag. Come on, cut him up.
Okay, so this is an image of the sun. Most of us probably don't give the sun a second thought, but if we did, this is the image we'd have in our head. So basically what you're seeing here is a plain, hot, yellow disk in the sky. But as we've already seen, this really isn't the case, as this video demonstrates. So the sun is dynamic and active. It's active on different timescales, from days to hours to years. So just like we have seasons and storms here on Earth, we have seasons and storms on the sun. The seasons on the sun can affect space climate, while the storms are the drivers of space weather. A good question might be, well, how can something on the sun affect us here on Earth? And that's exactly what I'm going to demonstrate with this next video. So what you're seeing here on the right-hand side is the solar surface, and you're going to see a massive solar storm, which causes a huge eruption. And when I say huge, I mean huge. You're talking about Mount Everest, amounts of mass traveling at millions of kilometers an hour out into the inner solar system, eventually interacting with Mercury, and then that blue dot on the far right is actually Earth. I want you to keep an eye out. There's going to be a counter that shows up on the bottom left-hand side of the image, which is actually measuring the density of material impacting near Earth. And you'll see just as the CME hits us, it redlines. I'm going to play it now. And so you'll see the explosion come off the sun to the right in the blue. Just there, it's traveling out to the inner hemisphere, just impacting Mercury, and just about now, it's going to start impacting the Earth, and that's going to redline. And when that redlines, we can have serious effects on the Earth. We can have communication issues, GPS issues, and also even blackouts. But I mean, we've already heard about this, but like, what causes all of this activity? So if you focus on this central active region in the center of the sun here, it's the area with the bright loops and points. What is the underlying cause of all space weather? Well, it's the magnetic field of the sun, which is exactly what this image shows. So what you're seeing here is a picture taken by the SDO satellite, the HMI instrument, and what the colors show is the different polarities of magnetic field on the sun. And you can see there's a clear correlation between the active region and this complex patch of magnetic field on the sun. So magnetic fields are the driver for all space weather. In fact, if it wasn't for the magnetic field, the sun would be that boring plain dot I showed you at the start. But like anything, if we want to understand magnetism, we need data.
Yes, we always need data, but in this case, we have a lot of data. Over the past 50 years, we've had a number of different instruments collecting images of the magnetic field of the sun. For our project alone, we had close to 1 million images of the sun available to us. But what we're lacking is consistent data. So all of these different instruments have slightly different calibrations. They might be looking at different spectral lines, the noise levels and saturation levels are different. Their position with respect to the sun is different. Some are space-based, some are ground-based. You can't just take an image from one instrument and compare it like that with one from another. What you're seeing here is an image of the patch of the sun taken on the same day by a number of different instruments, and you can very easily spot the sheer quality differences in these images. Newer instruments like SOT have incredibly high resolution, and you can see very small features of the magnetic field, versus older instruments like the Mount Wilson Observatory. The images come out very pixelated, and you can't make up any finer grained features at all. So if we want to study the small scale evolution of the magnetic field of the sun, we need high resolution images. But if we want to study the long-term evolution of the magnetic field of the sun, we need 40, 50 years of data. And at the moment, we can't have both at the same time. Now, improving the quality of some of these older images is not a new challenge. People have been trying to do this for 50 years. But only now we're starting to get some good results. And the reason for that is that we have new tools available to us now, primarily machine learning, that allow us to make a big contribution. So my team, which is made up of myself, Carl, Shane, and Xavier, who sadly can't be here with us today, was tasked with the challenge to use machine learning for cross-calibration between instruments and super resolution of some of the old images. And of course, all of this would have not been possible without our amazing mentors. All right, but first, let me take a step back. So what do you see in this image? This is an image of a human face. You can just about not make out anything other than maybe where the eyes and the mouth is supposed to be. But if we sent this through a network that has been trained on human faces, we can reconstruct an immense amount of detail and actually make out a proper face. At first, that sounds crazy, because given what we started with, there is basically no information content in this whatsoever. But the thing about machine learning is that computers are very good at detecting patterns in things where humans can't see patterns at all, especially when given enough data. All right, so this is the super resolution part of our project. But now on to transformation. So this is our lovely mentor, Andres, and what he looked like 8 weeks ago. This is what he looks like today. It's been a tough summer. It's been a hard summer. But jokes aside, using computers, we're able to transform one image to another based on our expectations of what we think something might look like. So if all of this is already available for natural images, we were wondering, can we do this for the sun?
We've run a lot of experiments and a lot of different architectures that all use deep learning. That is all state of the art. And we found one deep learning architecture that worked for us. And it's this one. This is the one that worked best for us. Essentially, it's a compression-decompression system. I won't go into any more details than that. So please visit our stand in the poster session and ask us questions then. What we essentially see is that on the left-hand side, we have a small magnetogram, but then it's super resolved to a larger image. So in order to, as a first principle, to see if we can even use machine learning to address the grand challenge of magnetogram super resolution, we wanted to use a downscaled image, a central patch in the sun, which is a magnetogram. So a downscaled image to itself using HMI, a single instrument. And so on the left-hand side, we have the bicubic traditional method. Thank you, James. On the left-hand side, we have the bicubic traditional method, which takes points, averages them, and interpolates between them. The second one, next to it, is the output of our super resolved network. And the third one is the target. So we see that if we take the difference between the output and the target, they look very similar. So this looks really good. But is it enough to really just look good? No. It has to be physically meaningful. Physicists won't just buy something that looks good. It has to have value. There has to be evidence of the physics behind something. So what do we mean by evidence? Well, we look at correlations. How closely does the output of our super resolution network compare to a traditional method, to a baseline, in this case, the bicubic baseline? So our super resolved method generates points. So these are pixel-to-pixel comparisons measured by the magnetic field in Gauss. And the best prediction would be along this red line, this diagonal red line. So we see that the prediction from our network is closely spaced along this red line. And it's much tighter spaced than the one predicted by the bicubic alone. So we're doing good. This gives us confidence to move on and do the next thing, to go cross instruments. And not only that, but to go full disk. So before we just saw one patch, and here there are over 1,000 such patches that together combine into one full magnetogram image of the sun. So the picture that you see now is the original MDI instrument, so the low resolution source survey. And our target in this case is again the HMI, now the high resolution image. So we're going in between a low resolution survey to a high resolution target image. And these are now overlaid over each other, so you can see the clear differences. You can see that there's a green tint on the MDI original, which means like a noise floor. And you see that it's not very well resolved, the MDI original. Like the HMI target has much higher resolution. So now when we apply our network, we see a dramatic difference. We see that here's the original MDI, here's the prediction of our network, and here's the target. Look how closely they compare. The noise floor is gone now from the original MDI image, and the regions that we see here closely line up with very nice resolved, with very powerful resolution. So this points that we have done an amazing job. We've all done an amazing job. And we're an ambitious, so can we do this for the sun? To answer Anna's question, a resounding yes. Yes, we can. Indeed, yes, we can. So we're an ambitious group. This is an ambitious project. We want to push things even further. We want to go to the original Mount Wilson survey, which is 50 years old, over 4 solar cycles. Each solar cycle is 11 years. And we want to modernize this. We want to take this magnetogram from Mount Wilson and make it modern at the level of HMI. So what are our big goals? Well, it's to make our code and our data public. It's to leverage machine learning for science. It's to change the current attitude of the heliophysics community toward machine learning and make it a viable tool. And it's also to showcase how valuable our data sets are for a lot of scientific use cases. One of these scientific use cases is provided by the Space Weather Operations Research. So here's a simulation of what happens when there is solar wind. So there's solar wind continuously coming off of the sun. You see this in green. And then you have this enormous burst, this shown in red here. Bam, wow. That's a huge sweep. So by giving a consistent set of these magnetograms over time, we want the space weather prediction centers to help us be space weather ready and be able to anticipate such a burst before it happens so that they can alert satellite operators and also the power grid operators on Earth. So we've made a lot of headway. We've made enormous headway in this project, and we've addressed a long-standing problem that hasn't been resolved for 50 years. And with this, the future of machine learning is bright for the heliophysics community and at all. Thank you very much for your attention.
How might we expand the capabilities of NASA's Solar Dynamics Observatory using ML? So take it away.
Thanks, James. Welcome, everyone. So we are the SDO team. My name is Shovik, and there's my colleague Valentina. So allow me to take you through the journey to the sun today. So what you see behind me is the image of our sun, the same sun that rises and sets every day, the source of our life on Earth. We often take this sun for granted, but have you ever wondered how and to what extent it affects us? Well, let's take a look. So what you see here is a movie that is generated by the extreme ultraviolet images of the sun. So just to let you know that the sun emits radiation in the entire electromagnetic spectrum. And these bright regions that you see, these are called the active regions in solar physics. So these active regions are the sources of the most energetic events in the entire solar system. And they affect us in a way that they can affect our satellites, our communication systems, GPS, and even astronaut health when they're in space. Living near a star such as the sun, which is so active, means that we need to explore and understand it better. So, precisely for this purpose, NASA maintains something called the Heliophysics Systems Observatory. That is a fleet of several different missions that constantly monitors the sun and its impact on the Earth. One of the flagship missions of this fleet is the Solar Dynamics Observatory. So that's our team name. So it was launched in 2010, and ever since, it has produced really high quality data in 9 ultraviolet channels that you see right over here with a 12-second cadence with a 4K by 4K pixel size. Not only this, it provides us with the measurements of the magnetic field and the velocity fields on the surface of the sun. So this is a huge amount of data that we have. Despite this, we are still unable to understand the solar variability, or rather, we are still unable to predict the solar variability. And that is because we have seen the sun from the Earth's perspective. So our vision is to enable deep space missions that will have SDO-like capabilities. And not only that, it should be able to observe the sun from multiple perspectives, from multiple vantage points, with efficient telemetry and data storage without compromising the scientific return. So what can we do? Okay, so as a part of the NASA Frontier Development Lab this year, we decided to solve some of the problems. The first one that we solved here is called the degradation problem. So what is that? So the extreme ultraviolet instruments that you see, they suffer from steady and continuous degradation over time in space. So you can imagine the situation, something like human eye cataract, where your vision gets dimmed as you age. So this is the same with these instruments. The current calibration techniques that we have are sounding rockets, which are expensive. At the same time, they are complicated and they are really infrequent. So before beginning this program, we asked ourselves a question. So can we design future instruments that can automatically self-calibrate? Well, the answer is yes. And machine learning paves the way. How did we do that? So our framework is based on a convolutional neural network, which takes in degraded images of the sun in different extreme ultraviolet wavelengths, and it helps to calibrate it itself by synthetically or by actually recovering the original images. So how does it do it? The heart of the whole neural network lies in the convolutions. So the convolutional neural network work by focusing on extracting features of a particular image. And in this particular case, what we think is that we hope that the network works by learning to extract the features that you see here, which are called the active regions. But to be sure that it is exactly doing the same thing that it is supposed to do, we have something here called the activation maps. So the activation maps, these are the activation maps from the second convolutional layer, or the final convolutional layer that we have. So we can clearly see that on top you have one of the input images, and in the second row you see that the convolutional layer really focuses on these features which resemble these bright active features that you see here. Not only that, it also efficiently is able to distinguish the foreground from the background. So it definitely works the way we think it is supposed to. So further, when we are certain, we check the accuracy of our model. So before that, before going into the deep network that we have, we compare our accuracy by how a standard astronomer would use and a method that could be available with the simple non-machine learning technique. With that, we find that the accuracy is about 54% within a certain level of tolerance. However, when we use the deep neural network, in this case, when we see the deep neural network and we feed it with images from a single channel, we see the accuracy shoot up to 75%. Surprisingly, when we have the deep network feed in the images from all the channels that we have in the AIA, or the atmospheric imaging assembly instrument, the accuracy is a resounding 100% within the given level of tolerance. So this is how we solve the auto-calibration problem.
So we have seen self-calibration is one solution we propose to enable deep space solar mission. What else is holding us back to enable this kind of mission? Let's think of what we have seen at the beginning, the amount of data. An experiment like SDO is producing about 2 terabytes of data per day. And let me give you an idea of how much this is. How many pictures do you take on your phone every day? 5? Maybe 10? Okay, let's say 10. In this case, it will take you about 800 years in order to accumulate on your mobile phone the amount of data the SDO is producing in one single day. And imagine an experiment like SDO in deep space. We would not have the same luxury. Downstreaming data from deep space is much slower, so it will take us about 5 years to transmit just 1 day of science data back to Earth. So what can we do? In this case, the solution that we propose is to synthetically reconstruct some images from a subset of the data. And we tried that, and the challenge we gave ourselves this year was to reproduce one wavelength from one SDO instrument by using only 3 other wavelengths. And these are the results that we obtained. In this slide, one image is the real one, and one image is synthetically reproduced. Can you guess which is the real one? Who is voting for the left? Okay, who is voting for the right? Okay, that's interesting. So the right one is the one on the left. So yeah, exactly, that was easy. So the difficult part is how we did it. So we use also in this case a deep neural network. In this case, a UNet architecture. Those of you that work in machine learning probably already heard about this architecture. It's usually used for image segmentation, especially on medical data. And the peculiarity of this architecture is the ability to learn large-scale features while maintaining information about the single detail at small scale. That is what we need in this case. In this case, we want to leverage features on the surface of the sun and cross-correlation between channels, but maintaining information also at small scale in order to be able to reproduce the wavelength we are interested in and that is missing. So these images really look the same, but what is good for human eye often is not good for science, because the physics of the sun might be in the smallest detail of this image, in the faintest one. And in order to address this concern and really evaluate how good we're doing, we actually look at the difference pixel by pixel of the generated images and the predicted images. And in the ideal model, we will get a completely straight line. And what we're able to get with a UNet architecture is what you can see on your right. And we can see it's not perfect, but it's already much better than what we can obtain with a simple linear regression. That is the image in the middle, and that was our baseline. So where are we after 7 weeks of very hard work? We think with our research, we planted the seed to enable solar deep space mission. These missions are really important. They will enable us to better understand the sun and to predict its effect on our planet. This is what we care about, and we will keep working on that. But what we realized along the journey is that machine learning has the power to completely redesign how we think about space mission and space exploration. Think about the same techniques that we have seen applied to what you care about. If that is satellite communications, Earth observing, or a lunar or a Martian mission. What we are laying here are the foundation for autonomous and machine learning powered space instruments. And our dream is to have a constellation of autonomous space weather satellites. What is your dream?
A final Living with the Star team, Space Weather, GNSS, they were asked the question, can we better predict atmospheric scintillations that negatively impact global positioning systems? Welcome, take it away.
Thank you. Let's start with a little video.
No,
Up there.
it said right. It said take a right.
No, look. It means go up to the right, bear right, over the bridge, and hook up with 307.
Make a right
Maybe it's a
turn.
shortcut, Dwight. It said go to the right.
It can't mean that. There's a light
I
there.
think it knows where it is going.
This is the
The
light.
machine
This
knows.
is the light.
Stop yelling at me.
No, it's not yelling. There's no light here.
The machine knows.
Well, is that on? Yeah.
The machine knows, but does it though? We trust technology with our lives, but technology is heavily susceptible on natural phenomena. Is there a way to actually predict when machines are not reliable? This is actually the task we set out to answer with predicting GPS disturbances. I'm Thanos, together with Garima, Kara, and Ed over there. Hi, Ed. We try to solve this question. Now, GPS is everywhere, from Google Maps to autonomous vehicles to trading to aviation. A lot of applications actually rely on accurate location and timing from the global positioning system. Actually, over the course of 20 years, $1.4 trillion of economic benefits have been added to the private sector because of GPS. But how does this machine actually work? The GPS receivers in your phones communicate through radio signals with satellites above the Earth's surface at about 20,000 kilometers up. Now, these signals get transmitted through the Earth's atmosphere and pass through a layer of it that is actually made up of charged particles, the ionosphere. Now, this ionosphere is actually heavily susceptible by space weather. We've heard a lot about space weather today, and let me define it a bit for you. Space weather is essentially the interaction of the solar wind together with the magnetic field of the Earth and also the upper layers of the Earth's atmosphere. So high energy particles originating from the sun get deposited on the magnetic field of the Earth at very high latitudes and create perturbations on the ionosphere. Now, these perturbations of the ionosphere can manifest themselves as one of the most spectacular natural phenomena we've ever seen, which is the aurora borealis, but also create GPS disturbances. These disturbances can be as simple as degraded performance, but they can also be as extreme as complete loss of signal. Now, because of the heavily dynamic and complex nature of both the solar wind, the ionosphere, and GPS, no physics-based model is able to predict accurately specific times and specific locations of GPS disturbances. But, Garima, do we have a solution for this?
Yes, we do. Our solution to solving this problem relies on a data-driven approach. Can we leverage physics and machine learning to predict these disturbances? Because as we know, machine learning can sometimes help us deduce patterns in the data that are otherwise very hard for humans to see. In this study, we use over 40 independent observed parameters measuring different properties of the Sun-Earth system, spanning all the way from the solar wind to the interplanetary medium and into the ionosphere. And we use all of them as inputs into our machine learning model. The biggest challenge in our study is that the peaks that we are trying to predict are extremely abrupt and sudden. So the blue lines here are the targets that we are trying to predict. So whenever you see a very high peak, that means that we have very high disruptions in the signals. And the reason why they are so peaky is because of the phenomena that's actually causing these disruptions, which are these small-scale abrupt ionospheric irregularities. And we're trying to predict these targets 1 hour ahead into the future. Now, the problem is that the conventional machine learning models treat these peaks as outliers. So we design a custom architecture to predict these disruptions, and we treat this problem as regression. Previous studies have treated this problem as a classification problem. So this is the first time that we are treating this as a regression issue. We have developed innovative training objective, which forces the model to forces the model to span the dynamic range of the target. And we also come up with innovative techniques to deal with the missing data because we have 40 streams of input data going into a machine learning algorithm. And we achieve promising results. The orange peaks here are our predictions, and the blue are the ground truth data. We are actually able to predict these disruptions with an accuracy of 5 minutes. And we have improved by 15% in predicting the timing over the previous attempts. We have also set a new benchmark for the magnitude prediction of these disruptions. Our model is pretty fast. It can be easily deployed and can be used for real-time performance as well. And the best thing about this model is that it is generalizable. So if we have a model that is trained at one location, and if we try to use it at another location, which is 1,000 kilometers away, it will do so. It will help us predict these peaks 1 hour ahead. But can we do better?
Yes, we think we can. So as Garima mentioned, this time series approach, this data-driven time series approach is already giving us state-of-the-art results. But we'd like to use additional information about what physics can tell us about how space weather is impacting the ionosphere. So as Thanos said at the beginning, one manifestation of space weather is this beautiful display of northern lights, also known as the aurora. And we know that the aurora is caused by some of the same physics that also leads to these local irregularities in the ionospheric electron density that lead to these disturbances in GPS. So one of the challenges that we set out to assess during the past 8 weeks is whether we can actually use images of the aurora in order to inform a predictive model and do a better job of predicting when these GPS disturbances will occur. So scientists have already observed that these disturbances in GPS are correlated in both space and time with the occurrence of the aurora. So that's what you're seeing in this video. You're seeing the magnitude of these GPS disturbances. This gives us a confidence that there is information in these images that can actually inform our model. But these images are fairly complicated to actually interpret, and machine learning is something that can really help us out with this, since machine learning is very good at predicting patterns in images and also giving us a way to process through a huge number of images in much faster than a human could. So one approach that we've used during the past 8 weeks is to actually just take images of the aurora, use a machine learning model to compress that information into a compressed representation, and then try to accurately reproduce images of the aurora. And using this compressed representation, we can actually map out how these images are related to one another and also look for which specific features in the aurora are important for which specific features in the aurora are actually more important for leading to these GPS disturbances. So this was actually an unexpected result from a machine learning model that agreed with what we expected from physics. So we saw that these specific arc and discrete structures in the aurora are more likely to be correlated with the GPS disturbances. Of course, what we've been working towards is actually including these images of the aurora into our predictive model. So it's not very clear how you would actually do this, though, because we have both image data and time series data. And the approach that we've come up with is to take a reduced representation of the images, pass it through several convolutional layers, then concatenate it with our time series data, and then use this as a predictive model. And we find that it does indeed improve our predictions, and that we can now predict more of when these peaks or GPS disturbances will occur, although we do find that there are also more false positives using this approach. So this is already very promising, but what we would like to work towards, and this is our vision, is that we can eventually predict at a single location, both in space and time, when these GPS disturbances will occur. This would actually eventually allow us to correct this in our GPS as it happens, and then nobody has to worry about their GPS actually leading them into a lake. So we just want to finish up by thanking Google Cloud for providing the computational resources for this work, as well as our mentors who came from SRI, Intel, the University of Oxford, and Element AI. Thank you.